Hi everyone, welcome back. In the previous video, we talked about the global definition of a geodesic in general relativity, and today we'll talk about the local definition of a geodesic in general relativity. Before the video starts, I encourage you to set the playback speed to 1.25. All right, so what do we mean by local definition of a geodesic? What is a geodesic? Part 2, the local definition. Okay. Consider we are in a curved space-time, in a curved space-time. I draw here an hypersurface, which means a surface of greater dimension than 2, because it's a surface of actually 4 dimensions, time, x, y, and z, in Cartesian coordinate, for example. So this plane, this hypersurface, is supposedly representing our 4-dimension universe. Okay, so consider you have a curved space-time, and at point P, you can define a vector V. Okay, that's all I will introduce. Now, imagine that we parallel transport this vector around a closed loop in this curved space-time. Okay, so imagine we parallel transport this vector V. So it will come here, then here, and here, and here, and here. Well, I don't know how it will look like because I don't have the metric for the geometry, but eventually, after being parallel transported around the closed loop, the vector will come back like this. So PT stands for parallel transported. And so the vector V coming back after being parallel transported around the closed loop will come back with a slight difference. It will not come back parallel to itself. This is something we observe from the curvature of the space-time. And it means that my vector V has not been parallel transported along a geodesic. So mathematically wise, we will write this as follows. The covariant derivative of my vector, my field vector V, in direction t at point P is equal to the limit of epsilon going to 0 of V at point P parallel transported minus the initial vector at point P divided by epsilon. This is the mathematically, yeah, this is just what I explained earlier. So here we have epsilon. Epsilon is because we are parallel transporting our vector V in a neighboring path around P. It means that epsilon is the length of this path, of this neighboring path. or infinitesimal loop on my curved hypersurface or hyperspace, I could say. So as we tend to, yes, to reach zero in epsilon, this is the definition of the covariant derivative. And the covariant derivative is the translation of everything I explained earlier with parallel transporting a vector and not coming back parallel to itself initially. If it comes back parallel to itself initially, then we can write our local definition of the geodesic, which is delta u in the u direction equal 0. This is the local definition of geodesic. I forgot to mention what do I mean by in direction t or in direction u. I mean that we are parallel transporting our vector v following the direction of the unit tangent vector to our neighboring path. Yes. So we parallel transport in that direction. That's why I write it here. Okay. So now we have a local definition of a geodesic. It's a vector that once it's been parallel transported around a closed loop in a curved space, it comes back parallel to itself. Then it means that the vector has followed a geodesic. This result comes from a generalization that we know. Consider now a flat space-time, flat space, sorry, so 3D Euclidean space. You know that between point A and B, and here actually is, here now is just a surface, just a plane. So, yeah, we know that the shortest path between A and B is a straight line. So now if I take any vector in A and I parallel transport it in the direction of the unit tangent vector, I know that when I will reach B, or I have something slightly better. So this is still to the Euclidean surface. If I start at point P and I parallel transport a vector V in direction of the unit tangent vector, I know that if I parallel transport it around it, it will come back parallel to itself. No, that's not what I wanted to say. Okay. Sorry, I'm sorry. Okay. But I think it was clear enough, my explanation here. Now there is something I would like to get more precise about. I talked about it in the first video, and I would like to come back to it a little bit. It is very important notion. It's the Einstein equivalence principle, because there is something we say now and that I said in last video is that free fall are geodesics. Why free fall are geodesics? I could not answer that in the last video. Free fall are geodesics because they follow the natural path of object through space and time, through space-time, sorry. They follow a trajectory with no preferred direction. So in Newton point of view, an apple on the ground was at rest, right? This apple was at rest. Now, in Einstein point of view, the apple that is falling from the tree is following a geodesic, and my drawing is could be better. Okay, so through space time, this is time evolving. We know that at t my apple will be here, and if it's falling at t plus delta t it will be here, and at t plus 2 delta t, etc. This trajectory is the natural trajectory of all objects, in the universe, or in space-time. It's the natural trajectory. Natural trajectory means no preferred direction. It's geodesic. For example, if we now consider flat space-time, so Minkowski space-time of special relativity, and I draw a space-time diagram, as I was trying to make the point here earlier. Here I was trying to make my point that we know from Hamilton's variational principle that a straight line between A and B is the shortest path through space. In Minkowski spacetime, a straight line is the longest path through spacetime, and this results from the geometry of spacetime, which we read in the metric. So any other word line will be a shorter path, but still the straight line are extremal proper time word line. So that's the global definition I talked about in the first video. Global definition of geodesic word lines of extremal proper time tau. And this word line is the word line of my apple at rest. So free falling. Okay. Now let's take this math that are a summary of the physical interpretation, which was the introduction of my video. Let's take this math. If you work out some algebra, you will end up with this. So nabla beta A gamma equal del beta A gamma plus the Christoffel symbols or gamma beta alpha A alpha. This you can write it if you work out some algebra and that you want the local and global definition to be consistent. So if you do some comparison, you end up with this general definition of covariant derivative. And now we know that my vector field A has been parallel transported along a geodesic if it equates to 0. So this is now the meaning of geodesic. Okay, so we got quite a nice mathematical expression, and we found again from our global definition from last video the Christoffel symbols, which encodes all information about the curvature from the line element or the metric of my spacetime. I will finish the video with the note that if spacetime is flat, we know that the Christoffel symbols vanishes. And thus, the covariant derivative is just the partial derivative of the vector field A. This is not a surprise. This result is not a surprise. The partial derivative of a vector field, and a vector field you can think about the wind map of weather forecast. They are vector field because at each point on the map they attribute a vector. This is a vector field. And when we take the partial derivative at some point P of this vector field, this is expressing, so del alpha P alpha is expressing the change in the vector field P in, in the neighboring, okay, I should zoom maybe, in neighboring region. So if you take, and this is a shorthand notation for del P alpha del X alpha, and now is the Einstein summation convention. Alpha, it will be del P T del xt plus, yes, plus the special components. But now, maybe I'm doing too much of a generalization and I might say wrong stuff, but this was just a shorthand for, I can write alpha del X alpha. Okay. So taking the partial derivative of my vector field at point P, and now I realize that it should be A at point P, yes, A alpha at point P. This represents the change in vector field A in the neighboring region of my point P. Okay, but this is flat. Now we have a curved space-time. So we see that the covariant derivative accounts for curved space-time through the Christoffel symbol. If we have a flat space-time, Christoffel symbol vanishes, and we find that the covariant derivative is just the partial derivative, which expresses the rate of change in a vector field in its neighboring. Now that we have a curved space-time, we also have to account around point P in the neighboring of P for the curvature of this spacetime, and this is done through the Christoffel symbols. So this is why you find again the Christoffel symbols in the covariant derivative. And the covariant derivative tells you how your vector field A change in the neighboring of P, accounting for the curvature of space-time. Because in this Christoffel are hidden the information of the metric ds squared, which is the geometry of your space-time. Okay, I think that is all I wanted to say. So thank you for watching. I hope I've been cleared, and see you soon. Bye.